Okay, in this video, I want to actually just focus on another technique we have for if we have complexified our equation and we have successfully guessed a particular solution to the complexified equation, and I know that the particular solution to my real equation is the real part of that, how I can actually find that. So I'm actually starting by saying, suppose that we have determined that the particular solution to our complexified equation is this, and I want to get to the real part. Now, up until now, I've just been applying Euler's formula to this, foiling things out, and then collecting my real terms and my imaginary terms to do that. And that's a perfectly acceptable way of doing things. If I then want to graph the particular solution, that in this case I'm saying is the real part, I generally want to use that trig identity so that I can convert it into potentially an exponential function times a transformation of cosine. This just gives me another option that sort of does that all at once. Okay. Now, if I look at this number right here, this coefficient in front of the exponential function, 2 minus 2i, I'm going to just graph that in the complex plane. In the complex plane, rather than having an x and a y axis, we have a real and an imaginary axis. So 2 minus 2i would correspond to that point right there. Okay. So a point in the complex plane corresponds to a single complex number. Okay. And essentially, the real part 2 and the imaginary part negative 2 would correspond to the x and y coordinates if this were just a point in the xy plane. So they correspond to what I think of as rectangular coordinates. Well, for this same point, I could find polar coordinates instead. And I'm going to do that making sure that I find r to be a positive value. So I'm going to let r be this distance and theta be this angle. Okay. I could also, if I wanted to, let theta be this negative angle. I'm going to choose the positive one. Doesn't particularly matter. Either one will work. Okay. Now, if I do that, I can see that basically I've got here this nifty triangle. This side is 2 and this side is 2. So the r value would just be 2 root 2. Okay. If I look for theta, well, my reference angle alpha here, I can see would just be pi over 4, because its tangent is 1. The acute angle whose tangent is 1 is pi over 4. So my theta would be 2 pi minus pi over 4, or 7 pi over 4. So essentially, my polar coordinates would be r equals 2 root 2, and theta equals 7 pi over 4. Okay. Well, I can write this number, 2 minus 2i, I can write it in what's sometimes called trigonometric form. Sometimes it's actually called polar form as well. I can write that as 2 root 2 times e to the 7 pi over 4i. Essentially, if I find polar coordinates, it's r times e to the I theta. Let's just see why that works. Okay, this is going to be 2 root 2 times cosine of 7 pi over 4 plus I times 7 pi over 4. But that's 2 root 2 times cosine of 7 pi over 4. Well, we're in quadrant 4, so it's positive. And then I can just use this beautiful reference angle here and say, okay, 2 over 2 root 2, it's going to be 1 over root 2, plus I times sine of 7 pi over 4. Well, we're in quadrant 4, so it's negative. But again, using my lovely reference angle here, I'm going to get the absolute value that I attach to that negative sign is 1 over root 2. Now, if I distribute that, those root 2's are going to cancel. I'm going to get 2 minus 2i, which is exactly what we stated here. Okay. So this just always gives me another way of writing a complex number. It's essentially r e to the I theta, where r theta are polar coordinates for my point. All right, excellent. So if I do that, let's see how that affects this particular solution. I can now write that as 2 root 2 e to the I times 7 pi over 4. That's just this part. And then I was multiplying by e to the 3it. So notice that becomes 2 root 2 times e to the I times 7 pi over 4 plus 3t. Well, that's going to be 2 root 2 times cosine of 7 pi over 4 plus 3t plus 2 root 2 plus, let's write the I first, I times 2 root 2 sine of 7 pi over 4 plus 3t. Now, if I wanted the real part, that's this right here. So it's 2 root 2 cosine of 7 pi over 4 plus 3t. So what that did for me is it gave me a different way of finding the real and imaginary parts, but when I got it, it was already just a transformation of cosine. Now notice if I'd been looking for the imaginary part, I would have gotten a transformation of sine rather than a transformation of cosine. I'd have a couple options there. I could leave it in terms of sine because I can graph a transformation of sine. Or if I'm trying to make it match, it's more conventional to give things in terms of cosines. I could just use some trig identities because I essentially know if I compare my graphs, this is sine and this is cosine. So I can view cosine of t as just being the sine graph shifted pi over 2 to the left. So that's sine of t plus pi over 4. Alternatively, I can view the sine graph, if this is just sine of t, I can view that as the cosine graph shifted to the right by pi over 2. So that would be t minus pi over 2. So if I had this and I wanted to write it in terms of cosines, I could just say sine of this is the same as cosine of that minus pi over 2. So just another alternative for how I can go from a complex solution to the real valued part or the real part or the imaginary part. One nice thing about this is it does take me to just a single multiple of cosine or sine rather than sum of each. I don't care what method you use for finding your particular solution. If you prefer to just use Euler's formula and FOIL it out every time, and then if you need to graph it so that you need to get it into a grapher-friendly form, you can use that mnemonic triangle that we've seen, totally fine. If you prefer to always write these numbers in trigonometric form and you always want to use this method, totally fine. Okay. There are times when I'm going to say, hey, you need to know all these techniques. Here, I don't care how you get there. You need to know how to get from your complex solution to your real solution, and this just gives you a second option.